Thank you very much for this invitation. I'm okay. So I'm not sure now where is my lecture. Oh, I'm so sorry. Okay, here. All right. So what I'm going to talk about, thank you very much, Mihai, for including me. I thought I could go there and be present in the room. We have somehow plans, and it would have been very nice, but not this time. We have to wait for another few more months, I guess, to be moving around. So I thank you very much for this opportunity in any case. So what I wanted to talk about is something that I've been developing in the last year with collaborators, essentially Kun Wang, which is a graduate student at the Cirm program at UT Austin, Anna Stekovich, which is from the mathematics department, Michael Abdel Malik, which was a postdoc at Oren Institute also, and Boris Breisman, who is here. I'm a copy on his side of a big funding that we have from DOE on plasma physics. And the project is on how to mitigate runaway electrons on a tokamak that may damage dramatically the wall of the tokamak. So I'm excited to show you what the tokamak is. Many of you are very familiar with this, and I will not talk about the runaway problem today. I will talk about something that I found it, it's still work in progress, and we are fine-tuning it, but I found it still extraordinary, or from my point of view, I've never seen anything like that before. And it's an effect that you get when particles start to interact within a plasma. It's a diffusive effect, and it's still where it's the magnetic field is dominant and very, very low electric field. And it starts a diffusion process, which is due to mean field. And that actually it's very interesting, and this is what I want to explain to this community, because all of you are really pros in kinetic theory. So what I found particularly interesting is that you get to see that even if you start with a coherent Gaussian-like state, the final state, it's going to be something that is very far away from a Gaussian and has a formation of a very strong anisotropy. And this is not due to space. It's really due to the interactions between the phase space on momenta for the velocity of the particles, and coupled with the mean field framework of the spectral energy that you have when you do the true mean field theory. So the resulting problem is a quasi-linear equation that is a coupling of a spectral energy wave mode with a probability distribution of associated to electrons. So just this picture is to give you, and this is what I want you to grasp from here, because the lecture is all about the framework on how you're going to do the calculation of the model itself, how it's derived and how we calculate. And so when you have a tori and you have this interesting or important symmetry, in which you have the poloidal magnetic field that runs in this direction, and then the toroidal direction that goes into what is called the helical magnetic field, and they call this the outer poloidal and the toroidal coils, and this is what actually drives by magnetization the particles, the motion of particles. And so that basically means that whatever you are going to be looking into the dynamics of the probability distribution has to be reflected with respect to this motion that you get to see here. And that was something that, from the point of view of the work I have done on kinetic theory, was really, really new for me. So it has been actually very interesting, right, and it still is. So this is, let me just tell you that this is the motion which traditionally people thought the magnetization along lines, and when you see these lines, it would be, things are going around, so that would be the direction when they are behind the toroid, or the central solenoid of the toroid. But in fact, those lines are wiggling, and what you get to see is that, and those are what they are generated, the magnetic field lines, are actually moving a little bit around. And so it's always, so you see in this lower motion, these deviations, which are, because this is a very unstable configuration, it's actually I call it resultant of the helical magnetic field that it's going to be moving, and while it's accelerating, what you have is that you always are going to be thinking that the magnetic component induces a sort of force into the system on which you have to split it within the poloidal and the toroidal direction, and those are going to be orthogonal at any given point. So let me then start by what get from our colleagues from physics, and as all of you know me, I'm not a physicist. I'm a mathematician, I'm a computational, an analyst, and so I've been trying to do a crash course of magnetic theory. I have done some contributions on magnetic fields with Mikhail Bostad, but that was the only thing except this new thing. So here is a postulate, and I will explain you the model, and that from plasma physics in tokamaks. And I'm taking this from a review paper published on nuclear fusion last year for a group of people working in this grand project. So the quasi-linear diffusion of magnetized fast electrons, and that means it's a relativistic regime, and that is something that it really is going to matter for the model, with velocity v that depends on the momentum. So results from a stimulated emission and absorption of waves via wave-particle resonance. When you read this, I mean, it looks kind of strange, but this is actually elements of quantum mean field theory that come into the process of taking this model. So the plot, from that point of view, this Clausius process can be conveniently described by the balance equations for particles and waves. And waves are these called quasi-particles if you start from quantum mean field theory. It's like, sometimes they model it for the BKW approximation, or by the quasi-particles using the Wigner equation and then taking hydrodynamics. All of that for us is going to be given, and you see it in a minute. And what we are really interested in is in the coupling. Then you have the spectral energy wave growth rate, which is this waves I'm talking about, and this is what I'm going to start referring the spectral energy growth rate, and I put it in green font because I want you to follow that the coupling is going to be anything that comes from this quasi-particles is the spectral energy, while the particles from the PDS in the classical sense, we understand collisional particles, are going to be a diffusion model whose coefficient are going to be entangled in between the two of them. And so they are related to the probability of electron to emit a wave with a frequency WKR, R is space, when the electron changes its parallel momentum from p parallel to p parallel minus this small deviation with respect to k parallel. And then you realize when you read the things, and it's not at the beginning it looks like this is impossible to do anything about it, but basically what it's saying is you are going to decompose from starting now into the momentum vector as much as the spectral wave vector with reference to a given magnetic field. Okay, so at this point the magnetic field is fixed, and we are actually decomposing the dynamics of what happens on this interacting operator into something that interfaces when the spectral wave energy growth rate. So you see the equations in a minute, but just start to think why I show you the picture of the tokamak. All I want you to understand is that parallel means parallel in the direction of the magnetic field, and orthogonal is orthogonal. So parallel is in the parallel component of the magnetic field. That's what we call the poloidal component of the magnetic field. Orthogonal would be, the toroidal component. So, so the quantum number is called the gyro motion, WC, which depends on the magnetic field. And if the magnetic field is strong, this quantum number of or the component of what they call the gyro motion frequency is of order of 1, much larger than the plasma frequency, and then it induces a very important translation. What it would be the classical resonance condition when you look at the dispersion relation associated to this motion, to the Hamiltonian motion that is mixing. Remember how you get dispersion relations. You have the Hamiltonian dynamics, and then you are going to be mixing the space with a spectral, or as we like to call it, the variable associated, the Fourier variable associated when you do the calculation of dispersion relations in any equation that is going to be mixing the velocity as much as the spectral variable. And what this number comes up here, as you see it at this moment, is that dispersion relation and corresponding resonant condition gets to be modified when this omega c, where the gyro motion is actually strong. Okay, and then in that concept, let me just stress that v of p, which is the velocity given a momentum, and so the velocity, if you see, I'm following the protocol of physics, that if you put a bold number on p, that's a vector. If you put unbold, that's the magnitude. And what it really matters is that the relativistic regime means that everything is renormalized, so velocities are going to be completely saturated because everything is renormalized by the relativistic factor, which is shown here. Okay, all right. So that induces that everything I'm going to be saying is going to be in a particular coordinate system, and this is relevant because it's a very important slide in the sense that it sets the framework of what they are doing. And I'm following this review and nuclear fusion 2019. If anyone is interested, it is available. I can pass there. I didn't add in my slides the references, but I can add the details. Okay, so we have a coordinate system in a space, and because it's a toroid, maybe many of you know it, is really a sort of it's a toroidal geometry, and then you have elementary toroidal and cylindrical geometry. This is actually the way they look at, except that you have this translation of the center of your radial component, because the radial component has to be something that is actually simulating what happens in the inner core of the toroid, where the magnetic lines are not crossing each other. Okay, so that is an ansat, and you have to take it or leave it. I put this picture, but what we call here the azimuthal angle phi here is taken to be zeta, and so please think of that as the azimuthal is the direction in the toroidal component. Then you look at the p momentum space, because we have to describe the velocity with the constitutive form I showed you in the previous slide in p momentum space, and then you are going to be decomposing the space in the perpendicular part and the parallel part. And the parallel part is actually the one that corresponds to the direction which is going to be the direction on the radial component. So it would be the direction that would be with respect to the parallel component in the direction in the poloidal direction of the magnetic field, while this one is in the toroidal direction of the magnetic field. And then, okay, so this is a decomposition. This decomposition is orthogonal, and that actually is very important as we are going to be describing the equations and the scheme. And so the vector, the k-space vector uses to represent the spectral energy density of a Hamiltonian wave function in cylindrical symmetry, also decomposes in k for the magnitude and k parallel, and S parallel is a parallel component in the direction of the renormalized field, and here it would be the renormalizing the parallel component of the field. So it would be B. Well, okay, so here is little b refers to the full field, and it has full magnetic field. It's poloidal and toroidal components we described, and alpha is the azimuthal angle associated to the spectral space. An important observation comes up now, and you will be maybe disappointed, but this is a fact, and we are really, even from the physics point of view, is not well calculated, the Hamiltonian dynamics and the coupling with the collisional theory. And this is something that I think is one of the paramount problems in magnetic theory, how to really incorporate interacting operators that actually can reflect what is going on inside.
So we have the pleasure to listen
the modeling
Sébastien
of particles interacting in
University of
Montpellier. So here is the observation. The dynamics of the quasi-linear collisional form that I'm going to describe next as a diffusion operator is calculated after the average in our space. The Hamiltonian dynamic, so an aspect of the Hamiltonian dynamics. The resulting kinetic dynamics is space homogeneous. And this is interesting because you said, well, what happens there? There would be electric fields, runaways, and so where is the space here? Well, it's all going to be transferred into different parts of the motions where you assume that you have a given field updated in time and for even the runaways at this point, and magnetic field is fixed in all this description. That said, that means this is really the beginning of a new theory. And I have to say that when we started to work on this with my collaborators and talking to Boris Preissman, who's a plasma physicist at the Institute of Fusion Studies in Austin, my impression is that there is very little done and very little that we can really grasp on what is done so far. But the equations and the models are in this nuclear physics review paper for
we hear you, I think.
Runaway mitigation. So Preissman was very interested in calculating what this particular model I'm showing you here is. So so I'm trying to see if I can do a better visualization to view. Okay, this is what I want. Okay. So all right. So then basically what we are going to be having is the following. We have a particle probability distribution in cylindrical symmetry, p momentum space using a spherical coordinates. Spherical coordinates. Okay. And theta is the polar angle, phi the azimuthal, and they are with respect to the magnetic field B. And polar is the p parallel, is the poloidal component, phi is the toroidal component, would be p perp, and with respect to the drawing that you saw in the first slide. So this model is, they actually look at the model of a diffusion operator, okay? However, the diffusion operator is modified by the diffusion term, and the diffusion term depends on a solution of a local spectral wave energy equation. And so let me read it, local spectral energy density, W of KT. So, I mean, you realize that now I drop the R, but I keep the time. Why is that? Look in a minute. of the Hamiltonian in cylindrical symmetry. So here is cylindrical versus here is spherical. For the k space vector in the coordinates k parallel, and alpha, and that's I described it in the previous slide, is given by this equation, which is an ordinary differential equation for the wave spectral energy, because that comes from the Hamiltonian dynamics. If I would have a space, I would have here more components, which are the derivatives of the space. But this is a wave equation that has been modified, so the space is dropped because we have average. But there is a modification to that ODE. It has a source term, and the source term depends on a factor, which is called the spectral wave energy perturbation factor, which expressed in cylindrical coordinates in the spectral space is given by an integration, right, of the resonance condition that ties up together through the dispersion relation, the connection between the momentum space, which is P, and the spectral space, which is whatever is in K. And it's all very much entangled, depending on the gyro motion frequency, right? And also proportional to the derivatives. So somehow it's the sort of a divergence form associated to the solution of the quasi-linear equation. So when you look at this, it's a true problem, as we like to call mean field theory. Remember that, for instance, when we do Vlasov-Poisson, when you put the electric field for the Vlasov-Poisson, it's not an external field, actually. It is going to be a field that is the gradient of the inverse potential associated to the charges in the Poisson equation, for instance. Well, here, the magnetic field is fixed, the electric field is threshold, is zero, but what really matters is the coupling with the spectral wave energy. So it's mean field theory, it's quantum mean field theory. This goes back to how people derive equations, integrate the spectral motion, and then have to do the coupling and the averages to get a resulting equation that actually is fully quasi-linear, because this diffusion coefficient D of W depends on the solution of this ODE, whose perturbation parameter couples with an element of the probability distribution function. This actually is interesting, because when I look at that, it reminds me of this work I've done with Ricardo Alonso and Min Bin Tran on the coupling of quantum Boltzmann gas in a state of gas to the average of the Gross-Pitayevsky solution, which is the for a Beck for Bose-Einstein gas. And then the play is not with respect to the external forces. The play is within the spectral energy that you get as you look at the particle the Hamiltonian associated to particle motions. All right, so here I have the quasi-linear operator. Let me show you what are the diffusion coefficients, because these diffusion coefficients, as I said, well, how do they depend on the on this quantity W, because you would have to start, say, with an initial data. We compute actually first the perturbation factor, then we compute the ODE, then we enter into the calculation of the PDF. So what is then the resulting diffusion coefficient? And you get to see them here. This is all well described in this review paper of, in fact, Brasman is it's the first author in that manuscript. And so what happens here is you get to see that the diffusion coefficients associated to the PDF, they are going to be expressed as a function of the spectral velocity. And here is a coupling that, and this is very interesting, here we have the solution of the wave function, of the spectral wave energy. Here is a factor that mixes the spectral energy and momentum, and I like to call this the elephant in the room. The calculation that you do is very sensitive to these quantities, and this is very kind of elaborated quantity to calculate. And that is all proportional to elements that depend on the dispersion relation and to the fact whether you have this L, it should be this same L, which is whether you turn on and off this factor. If L is 0, is actually, you would have a dispersion relation that would eliminate this. When L is equals to 1, you keep it that, and you sum the modes, okay? And what I'm going to show you today in the 2D simulation is that we chose, because that is what of a very important element is the calculation for L equals to 1. And you can couple all of this at all the stages because the decomposition that you get to see is linear at each step. And that is why it works. All right? So in other words, if I have, so let me put it in here. If I start with an initial data, I compute this gamma for the initial data, for the first step. Then I'm going to compute the solution of the ODE. This is actually very simple and it's easy. We work all of that with FEM, with finite element methods, although you could do many things for the ODE, but for the quasi-linear equation is important. And then we get here, right, we put this diffusion coefficient with respect to the initial time, and then we calculate for the next time, and it would be F in delta t to be the first time step, and then you have an iteration that every step has been linear. And I will show you that it really, numerically, we see stabilization. We have no analysis done yet. There is no analysis at the PDE level, but I'm hopeful that because of the numerics, they should be there. And I think it's a kind of interesting open question. Okay, so the quasi-linear diffusion operator written in weak form takes this structure. And this is interesting because you immediately see that the right framework to look at this motion is to actually use coordinates that you take it to be mu, the cosine of the poloidal angle, and it would be somehow so you can do P, which is the radial part of the momentum, and so it's a lowercase p, times mu actually would give you P parallel, and then you have the P orthogonal that you can calculate it through the difference of coming from this calculation. But also, it's very interesting that if you start with data, that is always P parallel. It's like what happens in kinetic theory when you do this kind of one-dimensional type of planar flows or reductions, right, of planar flow. Then you have a dimensionality. There is a symmetry that is maintained as you do the calculation of the even analytical calculation of the diffusion coefficient. So you can write the whole equations into this framework, which makes it much simpler to do I mean, when you look at the operator at this level, if you have pre-computed the diffusion coefficients, you realize that the calculation of this particular diffusion equation is not rocket science. So the only issue is to have an iteration that is robust and let you do that. Now comes the dispersion relation. And this is a little bit elaborate. It's something that I still have, trying to grasp all the components here. But I bring it to your attention because this is what generates this factor U of LP, that and L is, if L is 1, I have to put the frequency, the strong gyro frequency, and that is what I want to do to get something that is really a deviation from classical stable statistics. So let me just say this very briefly. So here what you do is you look at the corresponding wave polarization vector, you define it that way, and then you know that the wave polarization vector is actually satisfies a relation with these vectors, these factors n, and this is what we call, and so it gives a sort of a quadratic polynomial, right, on the components of this vector. So the vector here, right, is the one that corresponds to the it has components E1, E2, E3, and this vector E is actually, it's not a quadratic polynomial, it's a fraction, and so you have to calculate the associated the associated determinant to this matrix, or this tensor, sorry, the alpha, epsilon alpha beta here is the dielectric tensor. The beta direction is actually, the alpha direction is the component along the magnetic field, the beta direction is the orthogonal, so it shows the polarization vector. This is very elaborated, but what if you put together, and I want to show so you grasp the issue here. So this, the electric tensor that appears in the conformation on how you calculate the dispersion relation depends, all right, on these values alphas, which you would come through the calculations, we come into the equation of n through the components here that have this factor. The E1 is 1, and that's the cylindrical symmetry of the tokamak, but then you have this factor G, and you have this factor eta, but then G and eta depend on, look, the plasma frequency as much as the gyro frequency. And then here, this is data, but this is what is going to generate the case space. And this is what is going to generate then the form of U. And while this is crazy, we did a calculation for L equals to 1, assuming assuming that that we have a control of these numbers, okay? That you see, and the W itself, sorry, I call it W, this is omega P and omega C, and omega itself would be the solution of this determinant. Now, my student Kun Wang has been following some work of Breiman and Alienikov, and actually we did the calculations of this determinant in a reduced form. But what it really comes interesting here is that if you assume that the components of the spectral wave energy vector, which is this capital W, are split in parallel and poloidal components, and you assume that these are relatively of order of 1 numbers, then what you get is that if WC gets to be large, this resonance condition becomes actually a good approximation for small values of K, okay, for K order of 1, right? I'll show you a picture. And this is what is called the Whistler wave frequency mode. Whistler is because when they listen in the tokamak, they whistle. They just like something like that. Okay, so the ones that are independent on the gyro motion are basically the ones that correspond to the classical plasma physics, and this is called the plasma wave frequency. So here what you get to see is the calculation that we did for the elements associated to the dispersion relation, calculated these polynomials, and it was done masterly by Kun Wang using Mathematica, because after all, you're solving a quotient. I mean, it was a polynomial, so it's a rational function that depends on all these frequencies, and then you solve the roots of that polynomial, and you have 4 roots, and then it's a quartic polynomial. You can do that perfectly and compare it with the Whistler wave, which is the blue one. And it turns out, and you have to trust me, that is within the region of K. This is K parallel, this is K perp, in the region which is 1, 1. Actually, this is a very good agreement, and the closer you go to smaller Ks, even better. So the simulations that we have are with a Whistler wave, not with a full energy. But the caveat is that if you really want to do back to the good particle physics, you have to get here the 0, which actually we have not calculated it because Breitzman really wanted to see the 1, and see the effect, because on zero it's going to be more classical statistical mechanics. Okay, and so you will see the formation of a distribution. So here you have the comparison of those, and the accuracy, you get a good accuracy for the spectral variable component of the wave energy of order of 1. So how do you compute the system? Is this realistic to spec? Would they converge? So we started last year by the simplest form, and it's what is the one-dimensional quasi-linear system. According to Breisman, this is a solved problem, and there is a paper of Ivanov and Rostov in '66, which we saw something that we could reproduce. They had a numerics, and it seems to be, but it's a snapshot in a fixed time. But we can show that actually it was converging. And we followed the ideas from there, and we could reconstruct it in a modern kind of a scheme using a finite element type of approach. I mean, you don't need, because it's a space homogeneous, there is nothing about discontinuous Galerkin or whatever. Any finite element would do it, because it's, I mean, you can do it with discontinuous element. It's only, sorry, we can, you have to, we have the diffusion equation, so we have to be careful. But I'll talk about that later. So what is the issue here? We have the wave equation. We start with an initial data, calculate the gamma. Gamma in this 1D toy model, if you wish, is constant and depends only on the spectral wave energy perturbation. I mean, this is called the factor. It's only depending on the plasma. So it doesn't contain this simulation, the gyro force. But yet, you see what the mean field theory does to an initial data that is a Gaussian. Okay, this is what I want you to focus. So the local spectral wave energy amplitude, what I called W before, here it's called N. That's been in the files and then changes. So this is the spectral energy. But remember, green is the spectral energy wave function, and burnt orange, as I like to say, is the diffusion equation. And sigma here is the derivative of P. So remember, gamma, if you remember what was gamma, that was an important component. Gamma contains the dispersion relation, contains the U, and contains this factor that depends on the derivative of f. So actually, it's not that here I'm putting the same factor. So here, maybe I should have written differently. The gamma that I have in the previous slide is gamma times this factor, this sigma, because it's in 1D now. So I'm only doing like this radial motion along P, which it turns out to be, it's very interesting. It's going to be along an angle that is moving, as you see the 2D simulation, what you compare to. But what really matters then is that the diffusion coefficient, because it's in 1D, becomes an explicit formula that comes from the solution of this calculation, right? And so we know that the diffusion coefficient will take, actually, it's a really directly proportional to the wave number, where now K, the K, because the wave number here should have K, because N depends on K, right, has been changed because of the integration of the dispersion relation, and is proportional to the frequency of the motion divided by the momentum. So K and P as variables, their dot product ties up through the dispersion relation to a constant, or to a value K. So K is always inversely proportional to P. It's easy to see in one dimension. In higher dimensions, it's more complex. But then immediately we were able to say we can obtain this kind of system, and you have to be careful because the dP is calculated, right, directly by, you see what I did? We replaced the wave function here, evaluated on on the dispersion variable as a function of the momentum variable, you replace that into the coefficient that appears right into this equation, and you get a beautiful equation for the diffusion, because the diffusion and the wave spectral energy in the proper variable are basically proportional to each other, but some constants, and multiplied by 1/p. And we solve this. So the way we did this calculation, we put an initial condition, it's a Gaussian. It has to be deviated from 0. This is a technicality. You never put p at 0 because you are actually doing a fast electron motion. So things are deviated far away from 0 momentum. Particles are moving, and they're moving fast. And so we center at the p0, and p0 is usually much bigger than 0. I mean, we take 20 units in the scaling of the momentum space, and so take an initial time, which is rescale and improperly, and the variables, and then we get the evolution of the diffusion coefficient, the Quasilinear equation for this initial data that satisfies conservation laws. But the conservation law is not your classical. Mass is going to be satisfied, but we have to do this cutting at 0 and at infinite. You'll see, I'll talk about that in a minute. Or equivalently, what happens is the following. You have that the mass is going to be proportional, because this is an exact calculation from this diffusion equation, right? I mean, it's in divergence form, so you can really calculate this term. But here appears the diffusion, but the diffusion coefficient depends on the wave energy number, and the wave energy number is actually divided, and it's proportional to 1/p max. But here you have your f. So what was the catch here? Your f, the derivative of f, was shifted far away from 0, and for a finite momentum. So what you really care is that your domain of computation has to be such that is very well prepared for the initial data. So in other words, you have to compute in a way that the tails are going to dump this bad effect as much as this bad effect at the end points of your simulation. This is technical. We do have to cut off always when we do the calculations of the PDF on any kinetic solver. We have to cut off the domain. We really care about the tails being well inside the domain. Same thing here, except that here we have this 1/p or p square, like in the momentum and the energy. What really you have here is not that the mass is, well, the mass will be conserved along that you can see, but the momentum, as much as the energy, actually have a relationship between themselves that actually what is conserved is the sum of them. This is a signature of mean field theory. Same thing happens to quantum Boltzmann coupled to the energy from the Gross-Pitayevsky equation. It's exactly the same thing. You don't conserve any longer. It's not a problem. Here you have something. Can you compute and satisfy this conservation? Here is the conservation of energy. Same thing. You get to see these calculations. And again, you get to see that this will vanish, right, if you actually have well-prepared data and you compute in such a way that the tails of the distribution vanish at the end points, right, even they vanish quadratically. But if you put data that are Gaussian and your does not have a blow up, something that actually is starting to grow and losing, getting more moments and passing something that is above the Lorentzian distribution, then you will be doomed. But that doesn't seem to be the case, at least with initial data that is Gaussian-like. So here I discuss a little bit about what happened with the limits of the way we do the calculation of this P max and P min. And so that I would call a well-prepared data for the bound, I mean, not only initial data, but also boundary data. So you have to put these things carefully together. And the discretization is a classical FEM. Let me go a little bit faster, but this is what I wanted to show. And I think the exact numerics of are kind of trivial for this community, for this particular example, but this is what we get. And the initial data is here from P. The diffusion coefficient is almost 0 here, so nothing is happening in this direction. The diffusion coefficient takes this value of gamma and it propagates the PDF. And it really gets into, after, we did this calculation in time scalar microseconds, and they really stabilizes in this, what the physicists call a plateau. And this is a hot tail, it's nothing to do with, and we have the conservation properties, mass and total energy, total momentum and total energy. I know I'm running out of time. I just want to say a few things about it. If you give me a minute, 2 minutes, Jingmei, and I want to show the pictures. We did the 2D simulations, and again, orange is the diffusion problem, green is the dispersion relation. Now I'm going back to the original notation. We have this diagonal, the discrete linear system, both of them, so we can actually calculate the coefficients that are this diagonal. So for the spectral equation, it's a diagonal metric. So this is calculated in order of n very quickly. This is actually an order of n squared because the matrix is dense. Here you see the iteration. You start with initial data, F, compute gamma. For compute gamma, you compute W, go advance in F, and when you advance in F, advance in the spectral equation, and then you get to see the flow chart. I'm not going to talk about the specifics. You can read about how the advantage and disadvantage that we have with the grid. This is our first runs. We need to refine the grid, to improve the Runge. I mean, we are doing the time integrator with backward Euler. We wanted to see if it was working, and it does. And we calculated the diffusion coefficients, this with a given U, L is equals to 0, so the dispersion relation. And let me show you what do you get out of it. And we do a particular reduction of this particular weight function that depends on the differentiation of F, and UL is this function of PK, and that actually is an integration that is going to give us the spectral perturbation factor in K, and that we are able to reduce it from 2D to 1D, and it's an exact calculation. If we use the Whistler wave, we believe we can also do it for the computer. And here is the simulation in 2D. And let me give you this interpretation. You have an initial data, is well prepared. In fact, the original domain, you see it here, is from 0 to 30. So we actually cut, what you are seeing here is a little cut of this part of the domain. Here we are plotting in cylindrical coordinates. So you get to see this is P parallel, this is P perp. So here is a fixed angle. And then what we have is the Gaussian initial data. And here, after 250 time steps, we get to see this deviation. And the 500 time step, we get to see that everything is very stable. Even this maximum doesn't get to pass any value from here. There is no blow up, and there is the plateau. And the plateau is expanding about the sort of same P, and changing the angle here. These are the diffusion coefficients, and you get to see that at higher times, the diffusion coefficients tends to shrink, and that is what stabilizes the motion, and is actually start to stop the propagation. And then this is the calculation of the wave, the spectral wave, and we have an H theorem. This we have not calculated yet, but we did calculate the conservation of mass, momentum, and energy. And here you have that if you do the energy along, it's kind of high. We lose a little bit to the time integrator. We have to rerun all of this with perhaps third or fifth order Runge-Kutta. I believe it would actually get into the 15 microsecond time scale, 700, so 500 delta T's. It would be perfectly conserved. And the total energy conservation is this one, which is 0, but you see a little bit thing up. So with that, I thank you very much for your attention. And I love this picture. It was taken by a flying plane, very fast. Lots of electron-ion collision in the ionosphere. And I think we have room for new work for at least 100 years. For young people, it should be fine. So, and I'm very grateful to the funding from the DOE project on this. Thank you very much for your attention. All right.
Thank you very much.